So when we're looking at transforming or translating a graph, the parent function is like that basic thing that you got on that chart. So it might be the square root function, could be the square function, could be cube root, something like that. And it's that idea is that based on what's happening in the equation or what is added, subtracted, multiplied, we can tell what would happen to that graph. Would it move up so much? Would it move down a certain amount, left or right? Would it stretch it out, make it skinnier, or would it shrink it this way or that way? So there's various things that can happen here. So it's based on what's going on. So one thing we've got to remember is f of x is the same thing as y. F of x being the parent function means it's the big picture. Okay, x is still x, and you remember y moves up and down direction. X is going to move left and right direction. Okay, so that's going to help us kind of help remember what's going on. So we're going to start with just kind of listing out all of the different transformations that can happen. And we'll start with maybe the easiest ones, the translations of the vertical shift. A vertical shift where k is a number. Vertical shift is like adding something to that. So that might be like square root of x, and then on the outside of that be like plus 5. That would be a vertical shift. Okay. Think about it like this: you're adding to what y is. So y, if you add or subtract to y, it's going to go up or down, right? So if it's a plus, if it's plus positive, you're going to go up certain whatever that number is. If it's minus a number, you go down that much. Okay, so that's a vertical shift when it's a plus or minus something on the outside there. Okay, on the outside. Horizontal shift. Horizontal moves left and right, correct? So if it's horizontal, it's going to happen to x or y. X. Okay. If it's plus, it's left. If it's minus, it moves it to the right. But it's happening to the x inside of that parent function. We'll see this as we get to some examples here in just a minute. Okay. It's the opposite of what if it's plus, normally plus in the x directions to the right, but it's the opposite of that. Okay. Minus, normally that would be to the left. It's the opposite of that. Horizontal shifts. I think things happen on the inside the opposite way. What do you think there? Okay. Then you could have the transformations happening. Maybe you got a vertical stretch. If you're going to stretch something vertically, you're going to multiply some number times all the y values. A is a number, and it's technically greater than 1. If it's a stretch, it's going to be a bigger number. So might be a fraction, might be 4/3, but that's bigger than 1. Okay, so if you multiply all the y values by something bigger than 1, they're going to get higher, right? They're going to stretch out some. Okay, so a vertical stretch, the way I like to think about those is, I don't know if y'all ever played with silly putty when you're little. You may still play with silly putty now. But if you took we used to take it, and the comics would come in the paper. You always had the paper in the house. Nobody gets papers anymore. You press that silly putty on there and pull it up, and the ink would come up on the silly putty, and it had the picture on there. So that'd be like Garfield or Charlie Brown or something like that. And you could stretch it like that, and it would make the picture taller. So you could take Garfield and the fat cat and make him skinny by stretching it that way. So that's what a vertical stretch does. It stretches it and thins out the graph, makes them skinnier. Okay, so that's a vertical stretch. That number that you multiply by has got to be bigger than 1 for that to happen. Okay, a vertical compression. Or you might hear me say shrink. Vertical compression, compress something, you push it down, right? Or shrink it, you're gonna make it shorter. Vertically, it looks the same. The only difference is that number in front is a small fraction between 0 and 1. Okay, so like 1/2. If you half all of the y values, it's going to make it shorter. Right. So if you had a table of values and you halved all of the y values, you would compress the graph. You'd make it shorter. Okay, that's what a vertical compression. So it looks the same as a vertical stretch, but the size of that number in front is what decides if it's a stretch or a shrink. Big number, stretch. Small number, shrink. Okay, small number is in a small fraction of decimal. Okay. All right. Then we get a horizontal action, horizontal stretch. That's happening on the inside, and remember the inside is the opposite. So when you multiply by a small fraction on the inside, it's going to horizontally stretch it. Okay. If it's a small number on the outside, it's a vertical compression, shrink. On the inside, it's the opposite. So that's one thing that if you'll get that in your head that it's the opposite on the inside, it makes it make a little bit more sense there. So if you half all of the x values, but the y values don't change, it's going to stretch that graph, it's going to stretch it horizontally. It's going to make it go wider. Okay, as you go from there. All right, and then horizontal compression. Y equals same look, a times x, but you're dealing with a big number. Okay, if you double all the x values, and it's going to be a horizontal compression. A bigger number in there. It's the opposite. It's compression when it's a big number, shrink. And the inside, on the outside, it would be a stretch. Okay. All right, and then the last things that we could deal with are reflections. If you're going to reflect across the x-axis, it means you're going to go from here to here. You're changing the sign of all of the y values. So a reflection would be like multiplying by a negative on the outside across the x-axis. Reflection across the y-axis is changing all the signs of the x values. So you're going from x being a positive 3, change it to a negative 3, and it just flips it across the y-axis, moves it to the other side. Okay, so negative on the outside, it's a reflection across the x-axis. Negative on the inside, reflection across the y-axis. Okay, that's what we need to remember. Okay, so let's take a parent function, one of those from that chart, and then let's do some of the shifts and write their new equation. Okay, so I want to do that. So let's take the square function or the quadratic x squared. This is one of those on your quiz. I should have been able to recognize it. We know it's a parabola type shape. Okay, so it's easy to shift up, down, left, right because it's that shape all the time. Okay, so the first thing I want to do is I want to write the equation if I shift it down 5 units. Okay, so from what I wrote down there at the beginning, if I'm going to shift down, I'm going to add or subtract to the outside of the original function. So shifting that down 5 units, I'm taking x squared and I'm going to do something to the y values. X squared is the y values. and I'm going to go down 5 units, so it'd be a minus 5. So that would be the equation to shift this original function down 5 units, the x squared minus 5. So it takes that parabola shape and it says, oh, move it down 5 units, 1, 2, 3, 4, 5. Just scoots it down. That's all it does. That's what that transformation does. Okay. Question 2. We're going back to the original. So each one of these is like a separate problem for that one function. We're going to shift left 2 units. Okay. So we're going to take x squared and we're shifting it left 2 units. So I got to look at that and I think, okay, if I'm going to shift left 2 units, I'm going to do it to the x, and left would be plus or minus. Plus. And it's the opposite of what it normally is for x values. So x plus 2 squared. Yeah, I guess the generic form of transformations is like that. Like if you have everything going on, it's normally a minus sign in there. If you remember vertex form for parabolas in Algebra 2, it had a minus in there where the vertex was, and that's where that minus comes. That's where the opposite comes in, is that standard that it has a minus in there. It's a lot like vertex form for parabolas and vertex form for absolute value graphs. Those same ideas. Always the opposite on the x parts, because it's a standard of a minus in there. Okay. All right. Well, let's combine that. Let's do more than one move. So we did a vertical shift down, and then we did a left shift horizontally. Let's do something that moves in both directions. So let's shift up 6 and right 7 units. Okay. So if we're going to move up 6, that's going to do what on the outside? Add 6 on the outside. So we're going to have a plus 6 there somewhere. And then right 7, that's a left and right, so it's going to be on the inside. Moving to the right would be minus 7. And there's the equation. The shift, the x squared, the square graph, up 6 units and right 7 units. That's what it would look like. Okay.
Wouldn't you be plus 7 because you're going to the right?
Like it's opposite. X normally plus would go to the right. It's the opposite when you're doing your transformations on the inside there. It's going to be the opposite. So let's go to another one. Same. You're still staying with the squaring function. This works with no matter which parent function they start with. They start with the square root function. It's the same idea. It's going to be the inside is left and right, up down is on the outside. That sort of thing. Let's do a vertical stretch. By a factor of 4. Vertical stretch is just multiplying the outside by 4, right? It's a number bigger than 1. That's going to stretch it. It's going to make that parabola look skinnier, but it really is stretching it out. That's what it's doing. It kind of just, the bottom part stays at 0, 0, and it stretches it up from there. That's what that 4 does. The factor is what you multiply by. That's exactly right. What you just multiply by, whatever it says the factor is.
So if it gives you 4, so your equation is A times F of X.
Mm-hmm.
4 is A.
Mm-hmm. Absolutely. That's right. Okay. Let's do a horizontal compression. By a factor of 4. Horizontal compression. Horizontal is going to have them on the inside, so I know I got parentheses by a factor of 4. So normally, it's f of a times x. Well, a is 4 here. That. What vertical stretch would be the same thing as that? This is where it gets interesting to me. If this is a horizontal compression by a factor of 4, what vertical stretch would be the same problem? The graph would look the same. Can you simplify this with algebra? What's this work out to be? 16x squared. So the graph of this with the horizontal compression looks the same as a vertical stretch by a factor of 16. So when you look at a graph, it's hard to tell which one's going on. But with the equation, it's obvious which one's going on, if it's a horizontal compression or a stretch. But, that's the thing with graphs. You just get a graph, it's hard to tell what they did to it, because they could have done a horizontal compression by a factor of 4, or that's the same thing as a vertical stretch by a factor of 16. So you got to, when we're dealing with the equations, you can tell a lot more about what's going on than you can by just looking at graphs. Right? That's vertical compression. Horizontal's on the inside, it's the opposite. So it's going to be a big number on the inside for horizontal compression, small number on the inside for horizontal stretch. Okay. You can get your brain twisted around doing this. Let's do a reflection across the x-axis and down 4 units. Got more than one thing happening here. So if we're going to reflect across the x-axis, what do we multiply the outside by? A negative. So it's negative x squared, and then we're going down 4 units. So that would be minus 4. That's it. All right, now let's get to maybe a problem where if the point 2, 6 is on the graph of f of x. First question I want to ask is what would the ordered pair, spell ordered pair, O-R-D-R-E-D, be on y equals negative 3 f, I need parentheses, f of x minus 1. So we've doing a transformation here on that one ordered pair. Not necessarily on a parent graph, but just on that ordered pair. Okay. So you got to think about what each of those things is doing. The minus 1 is happening to the what? The x. The times negative 3 is happening to the y values. Okay. So if I subtract 1 from the x value, what's my ordered pair? 1. And then I would multiply the y value by -3, because that's what this transformation says to do. -18. So it's as simple as just plugging in the x and the y there from this y value.
How'd you get one?
Oh, so you times -3 by
Yes, by the y value of the original ordered pair. The ordered pair was, the x value was 2. I got 1 from saying, oh, well, 2 minus 1, 1. And then -3 times the y value. The y value was 6 to begin with, so I'm multiplying 6 by -3 in there, get -18. So you just take your ordered pair and do the work that it says to do to it. It's not anything crazy. It's actually easier when it's an ordered pair than it is when it's a function. Okay. Let's do another part to that. Let's say we had to do y equals f of x plus 4 minus 8. Yeah, get us the same ordered pair, 2, 6, and you do this work to it. You take x plus 4, so 2 plus 4 is 6. You take the y value and you subtract 8. 6 minus 8 would be, there's your ordered pair. You just do the work that it shows. Nothing crazy about that. It's really easy. Okay. All right. Let's look at the last example of the day. Or examples. We're going to take one -18. Let's describe the transformation on f of x equals the square root of x. Okay, so we're describing what's happening to the square root function. Okay, is it being shifted left to right, up, down, vertical stretch, vertical compression, horizontal stretch, horizontal compression, or reflection, any of those things that happen to it based on the equation that they give us. Okay, so here's our equation: f of x is equal to square root x plus 3 and then minus 6 on the outside. What did they do to the original function? Down 6, definitely down 6, because minus 6 on the outside. To the left 3, because remember it's on the opposite on the inside there. So left 3, down 6. And that's what I want you to tell me. If it left 3, down 6. If you wrote down 6, left 3, that's the same thing. It doesn't matter what order you write that in. Okay.
Just because of their addition sign.
That's right. If it's a minus sign, it means it goes right. Okay. Number 2, let's take that same function, the square root function. What do they do to it? The -3 and then the square root of x minus 5. Okay, right how many? Okay. What else? Nope. Not down 3 because they didn't subtract 3 on the outside. That's a -3 in the front. Vertical stretch or shrink? I heard both. Why stretch? Because the number is what?
Greater than one.
It's a 3. It's greater than 1. So it's a vertical stretch.
Wouldn't that be less than one?
The negative part does something else. What's the negative do? Across what? The x-axis. And maybe if I highlight each part. So the negative is this reflection across the x-axis. That's what the negative part does. The number 3, it does the vertical stretching. Okay. The right 5 is that -5 that's in there. That's what each individual part is doing. The negative out in front doesn't have anything to do with stretch or compression. It has to do with reflecting. Across, if it's out in the front, it's across the x-axis. If it were inside here, it would be across the y-axis. Okay, that's the way that's going to go. Let's look at another problem with this one. Same function, starting with the square root function. What did they do to it if you had this problem? -x plus 7, then a -16 on the outside. Down 16. So that's the -16 on the outside. That's the down 16. Left 7 is it's plus 7 on this inside. And reflect across the y. That's right. So the negative on the inside is this reflection across the y-axis. Okay? There's no compression or stretch there because it's not anything other than a 1 there. It's like a -1 in front of the x. So that's just a reflection. Left 7 plus 7 inside, and down 16 is from the -16 on the outside. Okay, so just recognizing what they're doing. There's a chart in your book on page 258 that kind of organizes this. You know, it's like what we wrote down on that first page of notes, but it's in a chart form that can help you maybe out of that. So in your book on page 258, there's a nice chart that can help you with that a little bit more, maybe organize it a little bit differently, and maybe it helps it make sense. All right, so suggested problems for this section be on page 260, where it starts 1 through 65. Just the various things that are going on with these transformations and things. You know, not going to get super complicated with them. You know, it's going to be very straightforward, a lot like what we've talked about today. Nothing just crazy about it. But it's transformations and translations. Now, some of you had this in Algebra 2, some of you didn't. So, there could be some, yeah, that would have everything going on. But you know, you just look on the outside to see what kind of stretch or reflection you might have there. On the inside, stretch or reflection or compression, and then shift left, right. And then on the outside with the plus or minus is the up or down stuff. So you just look in those same spots every time. It's never going to change which spot the vertical stretch or compression is going to happen at. It's always going to happen on the outside. The reflection across the x-axis is always going to be if it's a negative on the outside in the front. And the horizontal left shift left and right is always going to be the opposite on the inside. You're always just going to look for that plus or the minus in there. Plus would be left, minus would be right. And then the negative on the inside is going to be your reflection across the y-axis, the left and right. And then a number in there times x on the inside is going to be your horizontal stretch if it's a small number, compression if it's a big number. And then on the outside, plus is up, minus is down. Always, no matter what function you got, what original function you start with, the way the transformations work, they work the same on every different function. And whether it's the square root function or the cubic function, they all work the same way as far as shifting and transforming that. There. All right.